So we talked about the speed of waves on a wire, but we didn't talk that much about the way the waves can be set up in the wire. Let's say that you have a wire connected on both ends, okay, and you want to set up waves in that. Like say, I don't know, maybe on a guitar, or a violin, a cello, something like that. You can set up different waves in this wire right here, if you're having this fixed at both ends, okay, and you can look and see how the wavelength compares to the actual length of your wire. Let's call the length of the wire L. Okay. Now, the place where you're going to get the most resonance, which is where you get the music notes that we end up hearing from those string instruments, is when you produce a standing wave. A standing wave is a wave that looks like a wave that's not traveling anywhere, because it's going back and forth at a fast enough rate that it looks like it's standing still. So the first sort of situation that you would have for that would be a situation like this. Okay, if you have a string and you can pluck it, and you watch how it vibrates up and down, that's what you're actually seeing. You're seeing the standing wave moving through that wire. It's going this way, it's coming back, and going that way and coming back, but it's going so at a fast enough rate that it just looks like it's standing still. This is called a node, where it is at the equilibrium position, and this is called an antinode, where it's the maximum displacement. This would be the fundamental harmonic, the fundamental frequency at which this wire would vibrate. Okay? So we can look and see how that wavelength corresponds to the length. One wavelength, remember, is the length for one period. This is itself half a period. So the length is equal to half the wavelength, or lambda is equal to 2L. Okay. Now remember that the speed is equal to the frequency times the wavelength. So V is equal to lambda F, and where V, we said for a wire in a few lectures ago, is equal to the square root of the tension divided by the mass density. So that's equal to the square root of tension force divided by the mass density. And we can look and see what happens with this if we plug in lambda is equal to 2L and look at the frequency. F is equal to V over lambda, or 1 over lambda times the square root of the tension divided by the mass density. Or that frequency is equal to 1 over 2L times the square root of F, the tension force, divided by the mass per unit length. So now, if I want to look at the next wave I can set up in this, if I give it some more energy, I can excite a different state. And that different state that I'm going to be exciting will still have to be constrained by having nodes on both ends. Okay. So the next one that I would get would be this. But the standing wave part of it means that it's coming back, and you would see these two different fluctuations. This part is moving up and down, this part is moving up and down, this part is staying stationary. This is stationary, stationary, stationary. Now, how does the wavelength actually correspond? One wavelength is actually equal to the length. So in this equation down here, it now ends up showing that you have 1 over L times the square root of the tension over mu, because lambda is just equal to L, not 2L now. However, it's not the most useful way to write this. The most useful way to write this would be to actually keep this as 2L and multiply by 2 up here to compare to that. So that now it's actually equal to twice of the original. And if you look at the third one, which would end up looking like this, and you analyze the wavelength, you would end up with the frequency that's 3 times the original. This is called the harmonic series of the frequencies. So this would be the first harmonic, this would be the second harmonic, and so on and so forth. So you can label all the harmonics by an integer n. F sub n is equal to n times 1 over 2L times the speed of the wave, which we're being explicit and writing it as the square root of the tension force divided by the mass density, where n is equal to 1, 2, 3, etc. If n equals 0, well, you don't have anything anyway. So you start at 1 and you keep on going. But this would be the resonant frequencies you can set up if you have a wire under a certain tension and a certain mass density, or mass per unit length. So you can change the notes at which your guitar can do things if you have a tighter tension. That's why you have the screws, right, to actually change the tension in there. Or if you change the size, the density of those strings, that will also change the frequencies you get out of that. Okay. So we can look at the same thing with regard to wind instruments, or organs, also, if we're analyzing waves moving in air. Okay. Let's say that we're starting off with an air column, an air pipe with two open ends. So unlike where you had the string affixed at both ends and you have to have a note at each end, now because this is open, you end up with an antinode at both ends. So the first possible one you could have would be this situation here. Okay. So now we have to look and see how much of a wavelength do I actually have. We're going to still keep this as L. Okay. This is at an antinode, which means you still have this much of it out here. This is also at an antinode, so you have this much of it out here. So half the wavelength is actually inside the L. So L is equal to 1/2 of lambda, okay, or again, lambda is equal to 2L. Okay. But now we have to look at the fact that V is equal to F lambda again, and now V is just going to be the speed of sound in air, because all we're doing is propagating that wave through the air. So F is equal to V over lambda, which in this case is equal to V over 2L. Okay, so that's going to be our first harmonic that we're going to be talking about here. So if you end up now looking at the next harmonic, what are you going to do? You still have to start at an antinode and end at an antinode, and so you end up having to make two nodes in the center. Okay. And so now we have to actually look and see how much of a wavelength we have. Okay. And so again, this is at an antinode. This is also at an antinode here, but this will actually end up giving us a full wave right there. That's one period. You start at one place and go back to the same place. That's one full period of the wave, so that's one full wavelength. So now we have, in this situation, lambda is equal to L. So we're going to write this in the same way. We have F2 is equal to V over lambda, or V over L, but let's write it like we did before, 2V over 2L, or 2 times V over 2L. Okay? So you can see where this is going. The next one's going to have 3 nodes in the center, and the harmonic series for this is going to be Fn is equal to n times V over 2L, if you have the pipe open at both ends. But this is not the way all stuff works. You could have a pipe that's closed on one end. If it's closed on both ends, you're not going to get any sound out. There has to be some way for the sound to come out. So let's look at if we have a pipe closed on one end. So now we have an antinode over here, but when it hits the wall, it's got to be at a node. So it will come down. Oh, that's right. Apparently I'm having trouble drawing this right now, but we'll go the other way. That'll work better. Okay, so it ends at an antinode and starts at a node. So the question is, how much of a wavelength is embedded in there. Okay. If I extrapolate this out to be the rest of the wave, then what we have inside of here, if we divide this up into quarters, we actually have 3/4 of a wave that's in there. Okay. Now this is actually the second harmonic. What I should have shown you first, and not actually the second harmonic, because the second one you can set up in there, is that you first have this simpler case. Okay, because this still starts with an antinode and ends at a node. So this is L, but how much of a wave do you have in there? This extends all over there. You have to finish out the wave, so you only have 1/4 of the wave inside. So the L is equal to 1/4 of the wavelength, or V is equal to lambda F. F is equal to V over lambda. That means that the V over lambda is now equal to V over 4L. Now up here, we said for this case that we have 3/4 of the wave inside of the tube. So that means that the length is 3/4 of lambda, or the frequency, being V over lambda, is equal to 4/3 L for the denominator, which means that we end up with 3 times V over 4L. So this is going to be a different situation for the closed pipe on one end than it is for the two open pipes. For the closed pipe on one end, we see where it actually is going to have 1 and 3. Not 1, 2, 3, but 1 and 3. And so what ends up happening for this one is that you can only get the odd harmonics for this. That you end up with F sub n is equal to n times V over 4L, where n is equal to 1, 3, 5, etc. And that ends up happening because of the fact that you have this closed end on one side, unlike before where you have the two open ends for the pipe.